Hi everyone, so you tuned into a rather challenging question on second order differential equations. It's challenging because you've got to make a substitution, that one, not the easiest one to work with, and you've got to transform that differential equation into this one there. And then you've got to go ahead and solve it. You've got to go and solve that one in order to get a general solution for the original differential equation. You ready to go with this? Maybe you just got to watch this and see how it all pans out, or you've got to pause the video and have a go yourself. Okay. Good luck if you have a go yourself, but remember to unpause it and see the solution. Okay. Remember, at any point, if I say something that you're thinking, oh, not sure what happened there, pause, reflect, or go and watch one of my early videos. This is example 3, so I've got an example 1 and example 2, which maybe you should watch before this one. Okay, because it's quite difficult. Okay. So where are we going to begin? So we begin with this. Z is equal to sine x. That's our substitution. So straight away, you can find what dz dx is. So dz dx is just cosine x. We're going to use that somewhere. Now, let's consider our differential equations. So this one is in terms of dy dx. So I'll write that down, dy dx. And this one, we've got to transform it into, is in terms of dy dz. Okay? And I've just got an expression there for dz dx. Okay? So the challenge is to find a way of including all 3 of these derivative terms. Okay? And we have to use the chain rule to do that. So what I'm noticing is if I just multiply those 2 together, I've got dy dz multiplied by dz dx. That actually gives me dy dx. Cancel those 2, you get dy dx. So that is what I'm going to use, and that is my starting point. Okay, so I'm going to find the expression for dy dx, and then d2y dx squared, and then I'll be able to substitute them, hopefully, neatly into this to get that. That's my game plan, anyway. So, over the page, I've just written it up neatly. That's the chain rule we're using, and we need to set about finding dy dx. Now, dz dx is just cosine x, so I'm going to replace that there. That's what I need to do. So, dy dz times cosine x, that's pretty much it. That's dy dx done. All right. Now the next bit is I'm going to find an expression for d2y dx squared. So I need to have d2y dx squared equals something. Okay. In order to get d2y dx squared, I've got to differentiate both sides with respect to x. Now what that looks like is this. You're differentiating with respect to x, wrt x, and that means d dx of the left hand side and d dx of the right hand side. The d dx means differentiate with respect to x. So this one is easy because that's just something in terms of x anyway. The dy dx means that's in terms of x, so d dx of that will just be d2y dx squared there. This bit here is going to be the challenging bit. Okay, so you need to use the product rule for that because you've got a product of 2 terms. So v du dx plus u dv dx is how I remember the product rule, or in other words, that multiplied by the derivative of this added to that multiplied by the derivative of that. Okay, so the first one, dy dz times the derivative of cos x. I'm differentiating with respect to x, so cos x will differentiate to negative sine x. And remember, it's that times negative sine x, so that's going to be this. And then the next term is going to be that times the derivative of that, so plus cos x multiplied by the derivative of dy dz. Now dy dz is a bit more difficult because we're differentiating with respect to x. That is not an expression in terms of x. So we've got to use implicit differentiation here. Okay? So dy dz would be an expression in terms of z. If you think about it, if you have dy dz, that means you must have had something like, let's just make it up, y equals z cubed. So dy dz would be 3z squared. My point being, dy dz is something in terms of z. So when you're differentiating z with respect to x, here's how you write it, d dx of z, that's just, of course, dz dx. I'm just explaining to you why there's an extra dz dx that's just been tagged on the end there, okay? Of course, when you differentiate implicitly, you differentiate that under normal rules of differentiation, so d2y dz squared, but you must have the dz dx there, okay? That's the bit you want to replay again if you didn't quite get it, okay? Next up, I'm just going to simplify that a little bit. So I've got this here and that there. The dz dx there was cosine x. So I've got cosine x times cosine x cos squared x. Okay, so I've got that line there. In summary, you've got this. Notice how I stand away sometimes. That's just in case you want to take a screenshot without me in it. Okay. So in summary, we have dy dx, d2y dx squared, and we need to substitute into the original differential equation. Well, it looks like I'm just going to do dy dx, substitute into there, and d2y dx squared, substitute it in there, because I've just got those as the subject, so I'm just going to put them in as they are. So moving from left to right, so this bit here is going to be negative sine x dy dz times by cosine x, and then plus sine x dy dx. So that's going to be this bit here. Oh, sorry, I messed up. Beg pardon. That whole thing was d2y dx squared, wasn't it? Times by cosine x. Sorry, I confused myself there. Right, so yeah, that times cosine x, and then the sine x times dy dx. There we go, it's looking better. Sine x times that there, cosine x dy dz. And then this is just going to be the same, negative 2y cos cubed x equals to cos to the 5x. Then I'm going to see what I can do with that. Neatly, some of these terms cancel out. That often happens as a feature of these questions. Terms just cancel quite neatly. That's how you know you've got it wrong. Okay? So suppose I ended up with both those terms being negative, so none of them cancel out. Yeah, it wouldn't work. Okay? It normally works that terms do cancel out. Okay? So you just left with that one, and that one there, and that one there. So that's what we've got. Okay. So here we are. So we've got that there, and then we just need to try and get it in the form that we need. So notice you can divide that by cos cubed x. So I'm going to do that next. So you've got that just by there. Our answer has got to be, what was it again? Answer's got to be in terms of z on the right hand side. So let's just fast forward this again. So I need to rewrite that in terms of z. And if you remember the substitution there, the substitution was, I really should have written this up, z equals sine x. Okay, there we go. So z is equal to sine x. So you've got to think of a way of putting z back into that. We use the identity. Cos squared is 1 minus sine squared. Okay, so that's the next line. You've got 2, 1 minus sine squared x, and then you can write this in terms of z, because z squared will be sine squared x. So that will just be this, which is what we wanted. Okay. Right, now we need to go ahead and solve this. Okay, this is a harder one because it's not a differential equation equals 0. It's a non-homogeneous form, so it's a bit longer this one. Okay, so I've got some work on the board here. So start it off usual ways. Auxiliary equation, solve for m, positive or negative, roots 2. The general solution of that looks of this form, so we're going to write that up. So a e to the root 2x plus b e to the negative root 2x. Hope that's clear. Now that is our complementary function. That's part of the general solution because we do have a particular integral that needs to be found, and that's in terms of z. So not only do we have to find the particular integral, at the end we have to change it back, so it's not in terms of z anymore. Okay. For the particular integral, we need to try this. Why are we trying that? It's because this is the differential equation we're trying to solve, and the right hand side is a quadratic, 2 minus 2z squared. So the particular integral we need to try is going to be this. Okay, right, there we go. I just need to zoom out a little bit so I can fit all of this onto one page. Okay, so here we go. So differential equation to solve, complementary function is this. As I said, we need to find the particular integral. So for that, find dy dz, and dy dz will be this, and then find d2y dz squared. Let me just change that. Excuse me, dy dz squared. Look at how it'll be messy. If I get a chance, I'll re-record this video. If I don't, sorry, you've seen the bog standard first one with errors. It happens, it's a feature of my videos. Sometimes I make mistakes and I correct them and then I re-record. It just depends whether I get time to do it. Okay. Maybe this will be a video no one ever sees because I re-record it and I raise this one. Maybe you're a lucky one that actually gets to see this one raw as it is. Okay. I might just keep it actually because it's kind of special that way, isn't it? Yeah. So what we want to do next, substitute into the original differential equation. Okay. So nicely, we don't need that at all. There's no dy dz. So d2y dz squared, which is going to be this 2 lambda, and then subtract 2 times y, which was all that, equals 2, 1 minus z squared. And just expand the brackets and put the like terms together. So the z squared terms, and then the z term, and then the constants, and on the right hand side, just expand the brackets. So equating like terms, negative 2 lambda is equal to negative 2, because it's the z squared term, so lambda must be 1. And then the z terms, that negative 2 nu must be 0, so nu is 0 there. Okay. And then the constants, negative 2 nu plus 2 lambda equals 2. Bear in mind lambda is 1, that means nu must be 0 as well. Okay. And if that is the case, our particular integral must just be y equals z squared. Okay. So y equals z squared. So putting it together, the complementary function, you've got this as your general solution in terms of z. Okay. Now we need to get it back in terms of x. So just remember the substitution at the beginning was z equals sine x. So just replace it. So z, just replace it with sine x. And then you're done. Okay. Here's your general solution. Right. Hope you found that very useful. Thank you so much for watching. Okay. And I'll see you again. Bye bye. Now, do I keep the raw video or redo it with the? I'm going to keep this one. Okay. Kind of special, yeah. I'm going to adjust my display for classroom purposes, but I'm going to keep the original one. Okay. I'm sure at this level, if you've understood all of that, you'd not fuss about that little small error with the, yeah. So good, thank you. Cheers, thanks for watching. Remember to like, subscribe, follow, tell everyone about my YouTube channels. Okay, fair enough. Not many people can understand this for sure, if we're being honest. Okay, but it's nice to have subscribers and likes. Thanks. Cheers. Bye bye. You're all wonderful.